Welcome back. We are now in Chapter P, Section 3. This section introduces the idea of a random variable and the idea of a probability function. So, first, an introduction. Remember, in the previous sections, we talked about how calculating a probability is really just a counting problem. So we introduced the sample space, and to find probabilities, we would just count things in our sample space. So let's think about some sample spaces here. If we flip a coin one time, what is our sample space? Well, sample space is asking you what are all of the possible outcomes. If I'm flipping a coin, my possible outcomes are heads or tails. So that's my sample space. What if I flip a coin twice? What's my sample space now? You might be thinking, well, it's still heads or tails. Not quite. So if I flip two consecutive coins, or flip the same coin twice, I could see heads, heads, or maybe tails, heads, or tails, tails, and so on. So it turns out in that case there are actually 4 things in our sample space, so I have them displayed there. Okay, continuing on with this, what if we flip a coin 3 times? What's our sample space? Well, thinking through, okay, we could see heads, 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 tails, heads, tails, heads, heads, tails, 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 and so on. So we get a sample space with 8 things in it. Okay, let's skip ahead. Now I want to flip a coin 10 times, but I don't want you to list out I don't want you to list the sample space. I just want you to tell me how many outcomes are going to be in it. Well, when we flipped a coin once, there were 2. When we flipped a coin twice, there were 4. When we flipped a coin 3 times, there were 8. So there are 2 to the n things in our sample space, where n is the number of flips. So here it would be 2 to the 10th, or 1,024 things in our sample space. So that got out of hand pretty quickly. We would not want to write all of those out. But probabilities for this situation of flipping a coin 10 times are still things we could definitely be interested in. So that's where the idea of a random variable comes in. It's going to help us calculate probabilities without having to list things out and count them. It's going to make our life easier. So a random variable is a numerical quantity that changes from trial to trial in a random process. For example, it could be the number of pretzels in a jar of Martin's Party Mix. It could be the sum of 2 dice rolls. It could be the weight of a Siberian tiger. Or it could be a grade on the final for this class. And you'll notice that there's some notation here, so you're free to choose what letters you want, but random variables get capital letters, and typically we start with X, and then if we've used X and need another, we move on to Y. If we've used Y and we need another, we move on to Z, and so on. That's the convention, but you are free to choose other letters if you want. Now, a random variable can either be discrete or continuous. A random variable is discrete if it has a finite set of possible values. This usually happens if we're counting something, so it's kind of a hint. If you're counting something, it's going to be discrete. On the other hand, a random variable is continuous if it can take on any value within a certain interval. So it doesn't have just a finite set of values like 1, 2, and 3. It can take on any number between 1 and 3 to any number of decimal places. So it's got a whole interval that it can be. This happens when you're measuring. So this isn't a rule, there's obviously, I don't want to make an absolute rule just in case, but typically these are good hints. If you're counting something, it's going to be discrete. If you're measuring something, it's going to be continuous. So let's look at the 4 that I put up there. The number of pretzels in a jar of party mix. Discrete or continuous? Right, that's discrete. We're counting pretzels. The sum of 2 dice rolls. Right, also discrete. We're counting the number of dots on each die and then adding them. So discrete, and each die can only show, certain numbers. Weight of Siberian tiger, continuous. So there's not a finite set of values for that. It's more on a range. What about the grade on the final? And we're not thinking like A, B, C, we're thinking numerical grade. Right, continuous. So next up, probability function. By definition, a probability function assigns a probability value to each random variable. Properties, it's got some properties, so all probability functions have these properties, and it has to have all of them. It can't only have some of them. So this can be a way to check if something is a probability function, does it meet these qualifications. First up is the notation. So notation is important here. And to highlight that, I'm going to fix a typo of mine. First up is the notation. So the probability function for a discrete random variable, we're going to call it lowercase f of x. And if you're someone who likes to write all lowercase or all uppercase, this is going to be a chapter where you cannot do that. So lowercase letters and capital letters have different meanings here. So the probability function is lowercase f of x, and that is equal to the probability that our random variable x is some specific number. So that's what that notation on the right is. So capital letters is the random variable when it's still ambiguous. A lowercase letter, like that lowercase x, that is an observation of it. So, my random variable x is the number of pretzels in a jar of Martin's Party Mix. Say I go out and count it and I find that it's 12. The lowercase x is the 12. Capital X is the name of our variable. Next, this is a probability function. So as we saw in the first property, it is giving us a probability. Probabilities must be between 0 and 1, so the function needs to be between 0 and 1. And the function is equal to 0 for any value of x that is not in your sample space. So basically for any values of x that aren't possible. And we know, we've talked about this before, that the total probability has to be 1. So if you found the probability of every possible x and you added those all up, you should get 1. And we're dealing with discrete random variables here. This is for discrete random variables. And when we're in the discrete world, we call these probability mass functions, or PMFs. In the next section, we're going to jump in the continuous world, and that's going to be different. So, discrete PMF. Pair those up in your mind. We can do an example. We're going to flip 3 coins. So first, what's our sample space? We already found that on a previous slide. So we know there are 8 things in our sample space. We're going to define the random variable x as the number of heads in a series of flips. Specifically, a series of 3 flips. So x can be 0, 1, 2, or 3. Why? Well, look at your sample space. In the first one, we see there are 3 heads there, so okay, it can be 3. Next, it can be 2, still 2, still 2. Okay, now it's 1, still 1, still 1, then it's 0. So there can be 0, 1, 2, or 3 heads when you flip a coin 3 times. So we went from 8 things to 4. That's pretty convenient. Now here, 8 to 4, not a huge deal, but 1,024 all the way down to 11, big difference. Now, our probability function. Probability functions can be tables, graphs, or formulas. We're going to mainly focus, at least for this section, on tables. In future sections, we will talk about formulas. And we'll briefly mention graphs, but we're going to mainly focus on tables because drawing graphs on a PowerPoint is just not fun. So, our PMF is represented by a table. Your table needs to include 2 things. It needs to include x and f of x. So x, we said, can take on the values 0, 1, 2, and 3. So I have that on the top, and then on the bottom, f of x. So the probability of x being 0, 1, 2, or 3. Okay, now where did I get those? Well, look at x is equal to 0. So what's the probability that we observed no heads? If I look at my sample space, that only happened 1 out of 8 times. That's my probability. What about 1? Well, let's see. There are 1, 2, 3. Three situations in which we see 1 head, so 3 out of 8. Same thing for 2. And then what about 3 heads? There's only one way we can see 3 heads, so 1 out of 8. And all of these are between 0 and 1, and if we added them all up, they would be 1, so we're good to go. And that can be a good thing to do. If you're not sure if you were doing this right, a simple check is add them all up. If they add to 1, that's a good sign. And I made my table horizontal. You could make this vertical. Both are fine. So the graph of a PMF is called a probability histogram. And the way it works is on the x-axis, you have the possible values that x can take. And on the y-axis, you have the probabilities. So over on the left, we have a PMF table. Note their notation is a little different than mine. They have a p of x instead of an f of x. We're using f of x. And so x can be 1, 2, 3, or 4, so that's what I have on the x-axis. At each one, I have a box, and the box is, they're all the same width. It's the width of 1, and it's a height of the probability. So when x is 1, that probability is 0.1, so we get a box with a height of 0.1. When x is 4, probability is 0.4, so over there we've got a box with a height of 0.4. So that is how you make a probability histogram. So we can do an example, finding a PMF. Suppose Newton has a 4-sided die with the numbers 1, 2, 3, and 4 on it. Einstein has a 6-sided die with the numbers 1, 2, 3, 4, 5, 6 on it. And suppose each of the dogs roll their die once. So Newton and Einstein are my dogs. Let x be the sum of the number on Einstein and Newton's dice. So for example, if Einstein rolled a 1 and Newton rolled a 2, the sum is 3. We want to find the PMF for x. Now, if you can think through this in your head, awesome. If you can't, which I'll let you know I can't, it can be helpful to write it out. So we've made a table where we've got 1, 2, 3, and 4 on the left, and then up top 1 through 6. So if both dogs roll a 1, the sum is 2. If Einstein rolls a 4 and Newton rolls a 3, the sum is 7. So we just filled out what would the sum be for all of those. And now when we're counting and finding probabilities, we can count from our chart here. So here is our PMF. Again, we need x and f of x. So on the top, we need to decide what values can x take, right? So knowing what values of x are possible is part of this. And looking up there, 1 through 4 and 1 through 6, that means the lowest sum you could possibly see is a 2 if you add the 1s, and the highest you could possibly see is a 10 if you add the 4 and the 6. And you can see everything in between. So we've got 2 through 10. And now we need to calculate probabilities. So calculating the probabilities, first step, find your denominator. Notice there are 4 numbers and then there are 6 numbers. 4 times 6 is 24. So that's our denominator. Sorry about that. So our denominator is 24, and it is 24 for this example. So we look at that, and then we start counting, just like we did last time. So how many ways can we get a sum of 2? Looking at our chart, only 1, if both dogs roll a 1. How many ways can we get a 6? Well, let's see. If Newton rolls a 4 and Einstein rolls a 2, you get a 6. If both of them roll a 3, you get a 6. If Newton rolls a 2 and Einstein rolls a 4, you get a 6. If Newton rolls a 1 and Einstein rolls a 5, you get a 6. So there were 4 out of 24 ways that you could get a 6. So we did that for each number, and that's how we got our PMF. And if you add those all up, they should get you to 24 out of 24, so we know things are good. Up next, the cumulative distribution function. So the cumulative distribution function assigns a cumulative probability to each value of a random variable. So now, new notation and new what it stands for. So now this is a capital F of x. So lowercase f of x is the PMF. Capital F of x is our cumulative distribution function. And this is equal to the probability that x is less than or equal to some number. So you accumulate probability as you go across your table. And again, it's a cumulative probability, but it is still a probability. It needs to be between 0 and 1. And we've got some fun facts about it. The limit as x approaches negative infinity of capital F of x is 0. The limit as x approaches positive infinity is 1. And when we look at the graph, we'll see that. Also, if a is less than b, capital F of a needs to be less than or equal to capital F of b, because again, you're accumulating probability as x increases. And this has an acronym too. This is called the CDF. CDF. The graph of a CDF is a step function. So here we've got one, and first thing we can notice is the limit as x goes to negative infinity is 0. So that's why there's a black line extending forever to the left at 0, and up top, the limit as x goes to infinity is 1. We see a black line pointed to the right that would go on until infinity if this graph kept going. So those are those two limits. And now, how do we read the rest? Well, until you hit 0, there's no probability. Once we hit 0, it jumps up to 1/4. And then it stays at 1/4 until we hit 1, where it jumps to 3/4. And it stays there until we hit 2, where it jumps to 1, and then it stays there permanently. Okay, so we saw a graph of one, but how do you make that? How do you find the CDF? We can do an example continuing on with our 3 coins. So we had this PMF. We want to find our CDF. So here's our CDF. Again, we can use a table. We're pretty much going to always use either a table or a graph here. And we see it contains 2 things, x and capital F of x. Still on the top, x can still be 0, 1, 2, or 3. That has not changed just because this is a CDF. And how did I get those numbers on the bottom? Well, first, capital F of 0. That's the probability that x is less than or equal to 0. Which of our x's fall in that category? Just 0. So this is just the probability that x is 0, which is lowercase f of 0. Again, it's going to be very important to get the hang of the notation. I know there's a lot of letters and acronyms, but it's going to be very important to get used to those. Capital F of 1, that's the probability that x is less than or equal to 1. Which of our x's fall in that range? 0 and 1. So it's the probability of being 0 plus the probability of being 1. So add those 2 lowercase f's. Same thing, capital F of 2, probability that x is less than or equal to 2. What falls in that range? 0, 1, and 2. So add those probabilities. Lastly, capital F of 3, that's the probability of being less than or equal to 3. Which x's fall in there? All of them. So add up all those probabilities. And what did we say about what it should be every time we add up all of our probabilities? It should be 1. So the last entry in your CDF is always going to be a 1. Now, how do we use PMFs and CDFs to calculate probabilities? We'll do an example. We're doing this example strictly with notation. We are not getting a numerical answer. So when you have a homework problem like this, you're not trying to give me a numerical answer. You're not saying, oh, the probability that x is 3 is 0.7. You don't know that. You know nothing about the probability. We're just interested in how would I write this using the notation. So we have a random variable x, and it can take on the values 0 through 5. So using the PMF and the CDF, so just in F notation, find some probabilities. First one, find the probability that x is between 2 and 5 exclusive. So I don't have less than or equal to's there, which means the 2 and the 5 are not included. So what is included? 3 and 4. So using the PMF, this would just be the probability of being of being 3 or being 4, so lowercase f of 3 plus lowercase f of 4. Using CDFs is a little trickier. So again, I know I only want 3 and 4. So the probability of being less than or equal to 4 would give me 0, 1, 2, 3, and 4. But I don't want all of that. I only want 3 and 4. So I need to subtract off 2, 1, and 0. So I do minus the probability that x is less than or equal to 2. And we should recognize those from our definitions. That's capital F of 4 minus capital F of 2. Okay, try it again. This time, why don't you pause and try it without me and then see how you do. Okay, so now we're back. What is the probability that x is greater than or equal to 2 and less than 4? What falls in this range? Just 2 and 3. So using the PMF, that would be f of 2 plus f of 3. Using the CDF, it's capital F of 3 minus capital F of 1. Because capital F of 3 is everything 3 or less, so 3, 2, 1, and 0. But we don't want 1 and 0, so we need to subtract that off, and that's capital F of 1. So again, when you see this on a test or on a homework, when I ask it like this, just write it in F notation or, just using the PMF and CDF, and I don't give you any probabilities. You're just writing it using the notation. So we can also calculate the mean and the variance. So mean is a word we've seen before. Variance is a new one. The mean for a discrete random variable, also called the expected value, is given by this formula here. So the mean is mu, and we also have this notation E of x for expected value, and it's the sum over all of your x's of x times f of x. For example, here's a table, here's a PMF for probabilities about different scores on the AP Stats exam. We want to find the mean. So expanding that formula out, it's x times f of x for all of our x's, so 1 times f of 1 plus 2 times f of 2 plus 3 times f of 3, and so on. And we get that is 2.84. Now you might be thinking, oh, so it's a 3, right? Wrong. So yes, you cannot score a 2.84 on the AP Stats exam. But we do not round expected values. That doesn't matter. No matter what, we never round expected values. And so you'll see this, like if you Google how many children are in, an American household on average, it's like 2.3 or something. Can you have 0.3 of a kid? No, but we don't round expected values. It's important. So up next, the variance. Similar formula, and a new symbol. So we have a new symbol, sigma squared. You already know the symbol sigma, right? So sigma is your population standard deviation. Sigma squared is the population variance, and it literally is the standard deviation squared. So we also have a sample version of this, which is s squared, which accidentally made it onto your exam 1. So if you look back, you'll see an s squared in your symbols. So sigma squared, we've got this formula, x minus mu squared times f of x. And again, just to be specific with my notation here, I will fix this. So x minus mu squared times f of x, and you do that for all of your x's and you add it together. That's one formula, but there is an easier kind of shortcut-ish formula. This is the one I prefer to work with. You do x squared times f of x for all of your x's and add it up. And then usually if I'm asking you to find the variance, you've already found the mean. So you do that, and then you subtract off the mean. So take that sum and then subtract off the mean squared. It's a little less work for you than the first one, but you can use either or, they get you the same answer. So continuing on with our example, we've got our PMF for AP Stats exams, and up in the top I've written our formula so we can remember where it comes from. We want to find sigma squared. So we do 1 squared times f of 1 plus 2 squared times f of 2, all the way up to 5 squared times f of 5. So we do that, and then we subtract off mu squared. So you don't subtract off mu squared 5 times here, you only do it once at the end, and that's, you got to remember to do it. So if you do this formula, it's really easy to forget the minus mu squared at the end, so remember that. And we get 1.814. We don't round this either, but usually there's less temptation. And that brings us to the end of section P.3.